effect, the conductor disc must always move by itself, alone, or together with the magnet. In other words, in order to have induction, the conductor must always move, no matter how you combine it. Rotating the magnet does not induce a voltage. In other words, if you leave the conductor stationary, it will not induce a voltage. In this case, the B field is pointing downwards, the rotation is counterclockwise, and it induces a voltage from the outer rim to the center. On the right hand side, I saw the B field going upwards, so that's why the voltage is from the center outwards. But here you show two permanent magnets. A rotating conductor disc in a magnetic field produces a voltage from the outer rim to the center of the disc. The voltage polarity is according to the generator right-hand rule. Rotating a disc and a magnetic stationary, you get induction. Rotating the magnet and the disc stationary, no induction. Rotating the disc and the magnet together, you get induction. Okay, so this is an article that I want to show that there's two types of way of getting the homopolar effect. And the people in these articles, Rene Fugger, Arkady Matasaki, forgive me for mispronouncing their names, and John Kels. So in this article, they show there's two ways of getting the homopolar effect. The first method is called the disc method, which is a disc rotating in the B field. So the conductor is radial, in other words, the B field is straight, and the motion is circular. And the voltage induced is V equals BWRR for 2N surface, or V equals 1/2 BWRR for single end surface. Cylinder method, this is where along the surface of the cylinder the conductor is straight, the B field is radial, and the motion is circular. And the formula for the cylinder is V equals BWLR. L is this from one end to the other end of the cylinder. Disc area on two ends surface of the cylinder area on the surface along the length of the cylinder parallel to the axis of the cylinder. Cylinder induction equals V equals BWLR. Disc induction equals V equals BWRR for 2N surface. Disc equals V 1/2 BWRR for single end surface. V is the induced voltage per wire turn or segment. B is the magnetic flux density in Tesla. W is the rotational speed in RPM, revolutions per minute. L is the length of the cylinder in meters. R is the radius of the cylinder in meters. So basically this cylinder surface here, this is the cylinder surface, this is the white, and this is the disc area, which is the circular surface in blue. So the choice that I've chosen is the cylinder, and the formula is V equals BWLR, normalized to 1.88 volts per turn or segment. That's at B equals 1 Tesla, W equals 1800 RPM, L equals 100 millimeter, R equals 100 millimeter. Also, the induction applies to a single rotating conductor instead of a conductor disc. This is the disc method. There's a B field upwards, and the rotating conductor is clockwise. And now I'm showing the cylinder method with a single conductor. You have a magnetic field going from inside inner core rotor to the outside, the outer core, which is sometimes called the stator. And the key point to remember is the conductor must always move. Whether you want to move by itself, or together with the rotor, or together with the stator, or together with both the rotor and stator. This rotating together with both the rotor and stator is the preferred choice to minimize the air gap. The air gap then becomes only due to the conductor thickness. This way we don't need to have air gap so the conductor can slide. because everything is sandwiched together. We can rotate everything together. Since both are moving, the stator is called the outer core and the rotor is called the inner core. Now let's show the difference between a bar magnet and a disc magnet. Magnet stationary, conductor moving, voltage induced on the conductor. This case where the magnet is moving, the conductor is stationary, voltage is induced on the conductor. The third case where the magnet and the conductor moving together, no voltage induced on the conductor. Now comparing to the disc magnet stationary and the conductor moving, rotating, voltage induced on the conductor. This is the same as the bar magnet. But on the other two cases, they're different. The disc magnet moving, rotating, conductor stationary, no voltage induced on the conductor. Here, there's a voltage induced. This magnet and conductor moving together, rotating, voltage induced on the conductor. Here, no voltage is induced in the conductor. Why use Omopolar generator? Steady state magnetic fields, no frequency or changes of the field with time. Results in high efficiency, no eddy losses or losses due to frequency or switching magnetic fields. In a generator configuration, it's the only way to eliminate the motor effect. The problem is very low voltage is produced between the outer rim and of the disc and the center of the disc, results in I²R power losses, rendering it inefficient. Typically it is around 100 millivolts and we want to increase by 1,000 times to around 100 volts. Hence the need to come up with a way to increase the voltage, the high voltage Omopolar generator. Here's an example why using low voltage results in high power losses. Example, 10 volt supply with 0.5 ohms resistance in the transmission system. Say the resistance in the wires plus the supply source resistance, supplying 10 amps to a load. So there's the 10 volts, here's the source resistance, it's 0.5 ohms, and we want to supply 10 amps to a load. Let's assume an ideal case for comparison. The ideal case with no resistance in the transmission system, the power delivered to the load is power equals voltage times current, because 10 volts times 10 amps is 100 watts. That is 100% efficiency in delivery to the load. That's assuming perfect, no resistance. But with 0.5 ohms resistance, the power loss in the transmission is I²R, which is 10 amps squared times 0.5, which is 50 watts loss. And the voltage drop is 5 volt drop on the transmission. There's only 5 volts available to the load. So resulting is half of the power is delivered to the load, 50 watts, efficiency is 50%. But if we increase the supply voltage to 100 volts and we want to supply the same 100 watts to the load, the current required now is I equals power over voltage, which is only 1 amp. So in other words, deliver the same 100 watts, instead of being 10 amps, now it's 1 amp because the voltage is 10 times higher. Now the power loss is I²R, which is half a watt. So we only lose, now the efficiency is 99.5% efficient. So we went from 50% efficient to 99.5 efficient load, and no significant drop on the load voltage just by increasing the supply voltage from 10 volts to 100 volts to supply the same 100 watts to the load. The magnetic fields, here's how a cylinder method with the magnetic fields will come. Magnetic field comes from the side, which shown by the cross here, into the core, and then they come out radially out into the outer core. So the current on the conductors is coming out of the page and it flows in the same direction in all 4 conductors. It produces a magnetic field which is shown by the blue line, which is circular. And the magnetic field are orthogonal to each other. Therefore, this machine can only operate as a generator. Improvement to Omopolar generating increased the Omopolar device voltage. How to increase the voltage in your homopolar generator? By dividing the conductor disk or the cylinder outer shell into segments and connecting them in series. If we can divide one solid disk or one solid cylinder surface, which is equivalent to one segment, into 1,000 segments, and then be able to connect them in series, it will increase the output voltage by 1,000 times without having to increase the parameters in the formula. The total voltage becomes 1.88 volts times 1,000, because there's now 1,000 segments, becomes 1,880 volts. And if the current in each segment is 10 amps, then the output will be 18.8 kilowatts. T issues. You need to collect the current on all points along the circumference at the same time. The induced voltage, this is just summarizing, is too low. Solution is to divide disk into segments and connect the segments in series so that the voltage in each segment adds up. It's like the spokes of a bicycle wheel, not so easy to connect them in series. This is the example. This is a solid disk, which is in red. This is a permanent magnet, which is in gray. So if we take a slice out, a segment, the voltage induced in the segment is the same as the voltage induced on the remaining of the disk. A solid disk is equivalent to having many segments connected in parallel. Disk divided into 10 segments, the voltage induced in each segment is the same as the voltage induced in a solid disk. Why isn't it so easy to connect the segments in series? Cannot connect from outer radius of the previous segment to the inner radius of the next segment on the same plane. There will be an induction on this return path that will cause which will cancel the voltage induced. So we have here's one segment and here's the next segment. We want to go from this end to the inner radius, but this connection here also, because it's also under the magnetic field, will also have an induction on it, which then it cancels out. So we cannot connect them on the same plane. We have to figure out another way. Need to find a way to go away from the plane and to go away from the outer radius, go around and return through the center of the cylinder and connect to the next segment on the inner radius. In order to accomplish this, part of this return path need to be shielded. So find another way to connect in series by looping the return path through the center of the core away from the plane of the voltage induction. So what we do now is, this is the cylinder approach, which the B field is radial. So this is where the inductions occur. So we looped around through the center, and for the disk approach, the field is vertical and we loop around. So basically what we're doing is we're creating a toroidal core, but there's a problem. Connecting series by wrapping around through the center of the core would be factly creating a toroidal core. Can't find a way to apply the magnetic field such that the induced voltage adds up in series in a wire loop. The only solution is to shield certain sections of the wire loop where the induced voltage is opposed, the right-hand rule. So here is the disk approach, which is vertical. Here it induces the voltage shown by the right hand, but where the B field comes in, it induces the voltage in the opposite direction. Here's the cylinder approach, which is the B field coming in and going out. Again, it induces the voltage in the right direction here, but it's opposite direction here. So here is a simple representation. There's the conductor loop. This is like a cylinder where the B field comes in and comes out radially. The B field through the inside, this is called the insides, induces a current in the opposite direction to the B field through the outsides. No matter the combination you choose, the only solution is to shield either. We either shield the inside and use the outside for induction, or shield the outsides and use the insides for induction. So shielding, what shielding does is factly moves away the B field from the air, so it does not induce a voltage in the wire inside the shield. So for slots, so we're going to use slots for shielding. This is an example where this would be the inner core, this is the outer core, and this will be the air gap, and the magnetic field is diverted around the slot area. So if we're going to shield a certain section of the wire loop, might as well add the shield slot on the same plane where the induction is taking place. Shield the return portion of the loop by placing in the slots. So what we'll do is, instead of going all the way around, we'll just put slots on the same plane and just loop around the return path through the slots, which is shielded. This is the disc approach. This is the cylinder approach, where the B field comes out radially, and there's the slots. Induction still occurs in a shielded conductor. The slot provides a very good shield to the magnetic field, and there is no magnetic field present inside the slot, and therefore flux cutting cannot occur. However, research from prior experiments indicate that a voltage is still induced in the shielded conductor. Why? That is the subject of a later discussion. Anyways, this is how the first attempt was done. Was trying to build a device with the slots and shielded. We kept the slots with about 10% of the tooth width, so that will be very small. Slot width is very small compared to the tooth width. And this approach uses two ladder magnets to push the B field outside. And this approach does not work, so do not build this device. It will not work. And so this is more, so this is the end.